Hello everyone and welcome to our channel Techie. In this slide, we will see about the definition of homogenization. Homogenization is the process of breaking up the fat globules in cream to such a small size that they remain suspended evenly in milk rather than separating out and floating to the surface. A homogenizer is a machine which disintegrates the fat globules of milk. It is any of several processes used to make a chemical mixture the same throughout. It is intensive mixing of mutually insoluble phases, sometimes with the addition of surfactants, to obtain a suspension or emulsion. The process of homogenization was invented and patented by Auguste Gaulin in 1899. Homogenization primarily causes disruption of fat globules into smaller ones. In this slide, we will see about homogenized milk. According to the United States Public Health Services, USPHS, homogenized milk is one that has been treated in such a manner as to ensure the breakup of the globules to such an extent that after 48 hours of quiescent storage, no visible cream separation occurs in the milk, and the fat percentage of the milk in the upper 10% portion does not differ by more than 10% from the fat percentage of the remaining milk, as determined after thorough mixing. The number of fat globules in homogenized milk is about 10,000 times greater than those in unhomogenized milk. The size of fat globule is reduced to less than 1 micron, while normal fat globule size averages 2 to 12 micrometers in milk. The number of fat globules will be increased, but the total volume of fat globules will remain almost the same. The surface area of newly formed smaller fat globules is increased by 4 to 6 folds. In this slide, we will see about the principles of homogenization. In raw milk, the diameter of the fat particles varies from 2 to 12 micrometers, while a diameter of about 2 micrometers or less is required to keep the fat from rising in stored condition. The milk is forced at high pressure through a narrow slit, which is only slightly larger than the diameter of the globules. The velocity of milk in the narrow slit can be 100 to 200 meters per second. This can cause high shearing stresses, cavitation, and microturbulence. The globules become deformed, wavy, and then break up. In this slide, we will see about the homogenizing valve assembly. The homogenizing valve assembly is essentially an adjustable orifice, or series of adjustable orifices. The pressure created by the piston pump forces product through the homogenizing valve, causing a very significant pressure drop across the orifice. The well design and degree of pressure drop determine the effect on the product. In general, the greater the pressure drop, the greater the effect on the particle size of the product being homogenized. The homogenizing valve assembly has three crucial smaller components: the valve seat, and the impact ring. The valve and valve seat are the pieces that actually form the orifice. The impact ring is a sacrificial piece that prevents the high-pressure annular fan from damaging the chamber that surrounds it. All three components are made from a special wear-resistant hardened alloy. In this slide, we will see about homogenizer construction. Homogenizers generate high pressure using a piston pump with 5 or 7 pistons of the poppet type for better performance, and a homogenizing valve of the ball type to exert greater pressure. In this slide, we will see about the objective or purpose of homogenization. One purpose is counteracting creaming. To achieve this, the size of the fat globules should be greatly reduced. A cream layer in the product may be a nuisance for the user, especially if the package is non-transparent. Another purpose is improving stability toward partial coalescence. The increased stability of homogenized fat globules is caused by the reduced diameter and by the acquired surface layer of the fat globules. Moreover, partial coalescence especially occurs in a cream layer, and such a layer forms much more slowly in homogenized products. Another purpose is creating desirable rheological properties. Formation of homogenization clusters can greatly increase the viscosity of a product such as cream. Homogenized and subsequently soured milk, such as yogurt, has a higher viscosity than unhomogenized milk. This is because the fat globules are now partly covered with casein micelles in the aggregation of the casein micelles. Another purpose is recombining milk products. At one stage of the process, butter oil must be emulsified in a liquid, such as reconstituted skim milk. A homogenizer, however, is not an emulsifying machine. Therefore, the mixture should first be pre-emulsified, for example, by vigorous stirring. The formed coarse emulsion is subsequently homogenized. In this slide, we will see about theories of homogenization. One theory is turbulence. Sudden, high-velocity directional changes cause small intense turbulent eddies to form in the base liquid. Larger globules are torn apart by these eddies, reducing the overall average globule size. Another theory is cavitation. When traveling through the small orifice, the product experiences a considerable increase in velocity, then a sudden decrease in velocity and pressure. The rapid velocity and pressure changes cause the base liquid to suddenly vaporize, then collapse back into a liquid, a process known as cavitation. The imploding vapor bubbles further tear apart the fat globules. In this slide, we will further see about theories of homogenization. Another theory is shattering and impact. The fat globules are shattered by impinging them on the retaining valve or impact ring. Another theory is explosion. With the release of high pressure, the fat globules explode. Another theory is shearing and grinding. The fat globules are subjected to unequal forces as milk flows at different velocities in a fluid stream. As a result of the shearing action between globules, it deforms the fat globules beyond its yield point. Another theory is attenuation. The fat globule disruption is attributed to violent changes in the velocities of milk as it passes through the unit, rendering a fragmentation slight effect on the mean particle size. In this slide, we will see about types of homogenizers. One type is a high-pressure homogenizer. This type of homogenizer consists of a single-acting triplex pump with each cylinder having suction and discharge valves. The discharge valve of each pump empties into a common discharge pipe, in which a special valve is placed. The pressure ranges between 35 to 350 bars, depending on the type of construction of the valve. Another type is low-pressure rotary type homogenizers. Usual operating pressures are below 35 bars. The construction is so designed that milk is subjected to grinding and shearing action. Another type is sonic vibrators. Milk is subjected to high-frequency vibration in a device called a sonic vibrator or oscillator. In this slide, we will further see about types of homogenizers based on pressure. Sonic vibrators are low-pressure homogenizers operating at pressures below 35 bars. High-pressure homogenizers have pressure ranges between 35 to 350 bars. In this slide, we will see about the homogenization process. The homogenization effect is achieved by pushing liquid milk under a very high pressure through a very narrow orifice whose diameter is just slightly larger than the diameter of fat globules. When the liquid passes through the narrow gap, the flow velocity increases. The speed will increase until the static pressure is so low that liquid starts to boil. The maximum speed depends on the inlet pressure. When liquid leaves the gap, the speed decreases and the pressure increases again. The liquid stops boiling and steam bubbles implode or collapse. In this slide, we will see about types of homogenization. Homogenization can be complete, for example for milk, or partial, for example for cream. In this slide, we will see about full stream homogenization. Full stream or total homogenization is the most commonly used form of homogenization of UHT milk and milk intended for cultured milk products. The fat content of the milk is standardized prior to homogenization, as is the solid's non-fat content in certain circumstances. For example, in yogurt production. In full stream homogenization, the entire milk stream is homogenized. In this slide, we will see about partial homogenization. Partial homogenization is used to save on energy and machinery. The milk is separated into skim milk and cream, and the cream is homogenized and mixed with the separated milk. Partial stream homogenization means that the main body of skim milk is not homogenized, but only the cream, together with a small proportion of skim milk. This form of homogenization is mainly applied to pasteurized market milk. The basic reason is to reduce operating costs. Total power consumption is cut by some 80% because of the smaller volume passing through the homogenizer. In this slide, we will see about process requirements for homogenization. The physical state and concentration of the fat phase at the time of homogenization contribute materially to the size and dispersion of the ensuing fat globules. Cream with a higher fat content than 12% cannot be homogenized because it causes clumping and a shortage of membrane material or casein. Therefore, a good homogenization effect requires 0.2 grams of casein per gram of fat. The temperature during homogenization ranges from 55 to 80 degrees Celsius, and the homogenization pressure is between 10 to 25 megapascals, depending on the product. These are the general process requirements. In this slide, we will see about factors affecting homogenization. The temperature of milk should be above 33 degrees Celsius at the time of homogenization for the fat phase to be liquid for proper subdivision. The pressure of homogenization should be 10 to 25 megapascals. For milk with more than 6% fat, two-stage homogenization is better. If the broken up fat globules have a tendency to agglomerate, after the first homogenizing stage, they can be redispersed, employing 20 to 40 bars in the second stage. Homogenization becomes less effective with increasing fat content. When the fat content is high, raising the temperature improves homogenization efficiency. When the fat content is high, the newly created total fat globule surface is so large that the material plasma protein becomes insufficient to form new membranes on fat. These are the factors affecting homogenization. In this slide, we will see about the effects or advantages of homogenization. Smaller fat globules leading to no creamline formation, whiter and more appetizing color, reduced sensitivity to fat oxidation, more full-boiled flavor and better mouthfeel, better stability of cultured milk products, soft curd, no formation of a cream layer or plug, produces soft curd and is better digested, hence recommended for infant feeding. In this slide, we will see about the disadvantages of homogenization. Homogenized milk cannot be efficiently separated. Milk will not be suitable for the production of semi-hard or hard cheese because the coagulum will be too soft. Reduced heat stability in the case of a single-stage homogenizer, high fat content, and forms clumping of fat globules, more susceptible to sunshine flavor. In this slide, we will see about the application of homogenization. For fresh milk, creaming of fat is avoided and taste improvement is achieved. For coffee cream and evaporated milk, it avoids creaming and improves whitening power in coffee. For cheese milk, it reduces the fat content of whey, provides a more uniform fat distribution in the cheese mass, inhibits fat sweating of cheese, and enhances the biochemical fat degradation. For acidified dairy products, it improves consistency and taste, creates a more stable acid gel, and reduces whey synergizes in yogurt and other coagulated products. For milk mix beverages, it ensures good distribution of additives and fat. For ice cream mix, it reduces buttering of fat during freezing. In this slide, we will see about the effect of homogenization on the physicochemical properties of milk. Homogenization leads to a reduction of fat globule size. Reduction of fat globule size to less than 2 micrometers prevents the formation of a cream layer and increases the surface area of the fat about 6 times. Homogenization of milk increases its whitening power due to an increase in the number and surface area of the fat globules. Adsorption of casein micelles and serum proteins on newly created fat globule surfaces increases scattering of light, thereby causing a whiter appearance. Homogenization has been reported to improve the digestibility of milk due to an increase in the number and surface area of the fat globules. In this slide, we will see about the effect of homogenization on milk properties. Homogenized milk has a uniform flavor throughout. It tastes richer, smoother, and creamier than unhomogenized milk due to an increase in the surface area of the fat globules, which are uniformly distributed in milk. Homogenized milk is more susceptible to enzymatic activities, especially lipase action, than unhomogenized milk. Lipase can cause rancidity rapidly in homogenized raw milk. Homogenized milk is more susceptible to oxidized flavors caused by natural or artificial light than unhomogenized milk. To prevent the development of off flavors, homogenized milk must be packaged in opaque containers, such as cartons, plastic containers, or colored bottles. There will be an apparent increase in bacterial count after homogenization due to the breakup of clumps and colonies of organisms. Thank you so much for taking the time to watch this presentation. I hope you found the insights shared today valuable and informative. If you have any thoughts, questions, or ideas, feel free to leave them in the comments below. I'd love to hear from you. Don't forget to hit the like button if you enjoyed this video and subscribe to the channel for more content like this. Your support means a lot and helps us keep creating valuable content for you. Once again, thank you for watching, and I'll see you in the next video.